Swayam Prabha. Digital India. Educated India.
Any object in mathematics is well understood when we know what is its action. So the matrix A, we started like a static entry, but now A becomes a dynamic entry. Okay? It's a dynamic object. So it takes vectors, input as vectors, and output are also vectors. So it is a vector field. Okay, if B is a n by p matrix and A is m by n matrix, we will display the column vectors as b1, b2, bp. Yeah, these are the column vectors where they have n components, and A is a m by n matrix and B is a n by p matrix. Then we can define AB1, ABP by using this rule that I just displayed. A times B is A1B, A2B, AMB. Then we know what these vectors are. AB1, ABP, they are all sitting inside m-dimensional space. Yeah? And so we will define A times B as a matrix of size m by p, where the column vectors are AB1, AB2, ABP. Okay, so this is how matrix multiplication is defined. That the matrix A, which is on the left, is acting on the column vectors of B and giving us the column vectors of A times B. Okay, so we let A act on each and every column vector B1, B2, BP, and the resulting column vectors are AB1, ABP, and these column vectors, they constitute a m by p matrix. So there is a restriction here. A is a m by n matrix, and if we are multiplying on the right by a matrix B, it has to be n by p matrix. So number of columns of A is number of rows of B. Then only we can multiply A with B in this fashion. Okay, so therefore, if I display the row vectors of A and the column vectors of B as A1, A2, AM, and B1, B2, BP, then the result is this m by p matrix, where the first row consists of dot product of A1 and B1, dot product of A1 and BP. Then the last row consists of AMB1, AMBP, and it's a m by p matrix. Okay. Yeah. So that's how we are multiplying. So think of A as A consisting of row vectors. If we are multiplying A with B, display the row vectors of A, display the column vectors of B, and to write down the jth, the entry in the jth row and kth column, we will simply take the jth row of A and kth column of B and take the dot product and display the kth entry of the product. Yeah. So here are some properties. If I take a matrix A, which is m by n, a matrix B, which is n by p, then AB is a m by p matrix, and for j equal to 1 up to m and k equal to 1 up to p, AB, if I display the general entry of AB, which is Cjk is the real number which is obtained by taking the dot product of jth row of A and kth column vector of B, and therefore it is sum of sum varying from L equal to 1 up to n AJL times BLK. So just keep this notation in mind. If you know what it is, then it is clear. Okay. Yeah. So this is the, in terms of notation, what I just said. Display the jth row AJ1, AJL, AJN of A. Display the kth column. Take the dot product, that is AJ1 B1K plus AJ2 B2K, etc., and add them. So then you get the jkth entry, which is we write as Cjk. Okay. So product AB is defined only when number of columns of A is equal to number of rows of B. So we can't multiply arbitrary matrices. This restriction is there on number of columns of A and number of rows of B. They must be equal. And then A is m by n and B is n by p. Then A times B is a m by p matrix. Okay. Using this definition, you can check that if I have A m by n and I take a n by n identity matrix, multiply on the right, I get A. Similarly, if I take M by M identity matrix I and multiply on the right by A, I get A. A times 0 matrix, whenever the product is defined, is going to be 0 matrix. All entries will become 0. 0 times A will also be 0 whenever these products are defined. Okay, so identity matrix is kind of acting as the identity of multiplication, and but when you multiply 0 matrix with any matrix, you get 0, just like when you multiply 0 with a real number, you get 0. Okay? But we want to be careful about multiplying by matrices, because when you can multiply A with B in either way, that is, both AB and BA are defined, the product AB and product BA may not be equal. Okay. I'll skip this part. For you to practice, you should know how to multiply matrices. I explained how to do that. So if A has these 2 row vectors and B has 4 column vectors, you see that there are 3 components in every row vector and there are 3 components in every column vector. So take the first row vector and multiply by the first column vector to get the 1 entry of A times B, and that happens to be 2. And likewise, you can get all the entries of A times B, and the size of A times B is 2 by 4, because A is 2 by 3 matrix and B is 3 by 4 matrix. When you multiply them, 3 disappears and we are left with a 2 by 4 matrix. Okay. Both the products are defined if and only if A is a M by N matrix and B is a N by M matrix. Then only we can multiply A with B in either way. But in general, the product of A and B and A, they are not equal. Like the product of dot product of 2 vectors with same components are equal. It doesn't matter how you multiply them. And similarly, product of real numbers, it doesn't matter how you multiply them. The ordering doesn't matter. But with this definition of multiplication of matrices, it does matter how you write A and B. Okay, so AB is not equal to BA. For example, just take this very simple matrix, 2 by 2 matrix with the lonely entry 1 and other entries are 0, and B is the this matrix 0 1 0 0. You just multiply and check that AB is this matrix while BA is the 0 matrix. AB is not the 0 matrix and BA is the 0 matrix, so AB is not equal to BA, right? So AB is not equal to B, right? You can just check that AB equal to B, but it is not equal to 0. Okay. So if A and B were real numbers and B was, you see that B is a non-zero matrix. So A and B are non-zero matrices. Their product is B, but we cannot cancel B from this equation AB equal to B, because if you could cancel, then A will become the 0 matrix. But it is not the case. Yeah. And since A is not the identity matrix, we see that the so-called cancellation law doesn't hold. So if I write AB equal to B, you don't cancel B. Okay, we will see that sometime you can cancel B. Yeah? But in this case, if you cancel B, you will get a contradiction that A is identity matrix, which is not the case. Okay, so be careful. Cancellation law doesn't hold in the matrix multiplication operation. Yeah. So suppose I have a matrix and I want to extract the column vectors or row vectors of the matrix. This is required for many applications. I have large data set and I arrange it in the form of a M by N matrix. And many times I am interested in the first column or the second column or certain row. Then how to program the computer so that the output will be column vectors or row vectors. So this is achieved by matrix multiplication. So take these column vectors, basic column vectors, E1, E2, should have been EM. The matrix is M by N and the column vectors have size N. So I can multiply A on the right by EK. A is M by N and EK is N by 1 matrix. It's a column vector. So AEK, you can just check that it is the kth column of the matrix. Yeah, just use the definition of product of matrices. So EK is a matrix and A is a matrix, and this product is a column vector, and this is the kth column vector. Yeah. So given my M by N matrix and I want to extract the first column, you simply multiply A on the right by E1. You want to extract the second column, multiply A on the right by E2 and so on. So this operation will give you various column vectors of A, and this is important to display the column vectors. And by symmetry, you can extract the row vectors of A, and so to get the row vectors of A, I will multiply A on the left by row vectors. So corresponding to basic column vectors, we also have basic row vectors. So if E1, E2, etc. are the basic row vectors, then E sub k times A will be the kth row of A. Okay. So multiply A on the left by basic row vectors, then I get various row vectors of A. Multiply A on the right by basic column vectors, I get various column vectors of A. Okay, this is clear from the definition of matrix multiplication. So suppose I take two matrices A and B, both have same size, then their column vectors will be identical. Their row vectors will be identical. So if A equal to B, then all column vector, first column vector of A must be first column vector of B, and that is indicated by writing AE1 equal to BE1. Similarly, second column vector of A is second column vector of B, and then we write AE2 is equal to BE2. So A equal to B if and only if AEK is BEK. Yeah. So think of this A and B as dynamic objects, right? They are defining functions. A is a m by n matrix. It takes input as vectors in Rn and output as vectors in Rm. Yeah. So if this action of A and B coincides on the basic column vectors, yeah, basic column vectors are analogs of in the three-dimensional space. You look at the unit vector in the x direction, which is I, unit vector in the y direction, which is j, and the unit vector in the z direction, which is k. Okay. So if I have a vector, if I have a quantity vector whose action on these basic column vectors are same, then these two matrices or two vectors are one and the same. So A equal to B if and only if the action of A on kth column vector, basic column vector Ek is same as the action of B on the kth basic column vector Ek. Yeah. So now let's look at three matrices ABC, and alpha is a real number. It's easy to see this property. This property of A plus B times C is equal to AC plus BC. So matrix multiplication is distributive, yeah, on both the sides. So C times AB, A plus B is CA plus CB. And since the matrix multiplication is not a commutative operation, we have to display both these distributive laws, right? So when I write C times A plus B, I cannot write AC plus BC because AC may not be defined and BC may not be defined. So keep the ordering as same. A plus B times C is AC plus BC, and C times A plus B is C plus CB. And with respect to scalar multiplication, we have this property that alpha A times B is alpha times AB equal to A times alpha B if the sums and products are well defined. Okay. Uh, so here is a important rule which is corresponding to associative law of product of real numbers. So I have three matrices. A is a m by n matrix, B is a n by p matrix, and C is a p by q matrix. Yeah, I can multiply A and B. I can multiply B and C because number of columns of A is same as number of rows of B, and number of columns of B, which is P, is same as number of rows of C. And I multiply B and C in that order, and then left multiply by A, that is same as AB times C. Okay. So ordering is very important here. A times the product of B and C is same as product of A and B times C. Okay. So matrix multiplication, as you saw, it is defined in terms of dot product of row vectors and column vectors. But the and matrix multiplication is not commutative, but the associativity, fortunately, is true. Yeah. So matrix multiplication is an associative operation. I will leave the proof for you to check This comes simply by putting the definition of matrix product. Okay, and so you can write down the definition, and you will see that both these matrices are equal. So to prove an equation of matrices, I have to prove that the JK entry of the matrix on the left is same as the JK entry of matrix on the right. So we write down the definition of JK entry of AB times C and A times BC and show that they are equal. So two matrices are equal if and only if every entry in the jth row and kth column is same as every entry in the jth row and kth column of A times B times C. So this is easy proposition. I will leave it for you to read. These are some more properties of matrix multiplication. That if I have two matrices A and B which can be multiplied, then the transpose of A times B is the product of B transpose A transpose. Now you pay attention to the ordering in which we are writing. So A and B can be multiplied, right? But then B transpose is a P by N matrix and A transpose is a N by M matrix, and so I can multiply B transpose and A transpose. And transpose of A times B is same as B transpose times A transpose. The ordering is changing here. Yeah, you will not write AB transpose as A transpose B transpose, but it is equal to B transpose A transpose. So here is a proof. Write the entry JK entry of A as AJK and JK entry of B as BJK and the CJK as the entry JK entry of A times B. Then A transpose will be AJK prime, B transpose is BJK prime, and AB transpose is CJK prime. So simply display the general entry of all the three matrices here: AB transpose, B transpose, A transpose. Yeah. Then we, using the definition of matrix product, CJK is the entry in the jth row and kth column of A times B. To get CJK, I have to take the jth row of A and kth column of B and multiply them. So CJK is sum of AJL and times BLK, as L is varying from 1 up to N. Similarly, CJK prime. CJK prime is the JK entry of AB transpose. So JK entry of AB transpose is KJ entry of A times B by definition of transpose. So we write the KJ entry of A times B, and KJ entry of A times B is actually CKJ, which is sum of AKL times BLJ. Okay, and similarly, you can take B transpose A transpose. I know the entries of B transpose. I know the entries of A transpose, and when I write the product, so I can display the entry in the jth row and kth column of B transpose A transpose. That will be jth row of B transpose. Jth row of B transpose is really the jth column of B, and kth column of A transpose is kth row of A. So we just write down the definition of DJK using the product formula, and you can check that DJK is CJK prime. So that is the proof that transpose of AB is B transpose A transpose. I simply wrote the definition of an arbitrary entry of product of two matrices in terms of dot product. Yeah. So if you keep that definition in mind, you can write down the proof very easily that the transpose of A times B is the product of B transpose A transpose. So the ordering is reversed. Please keep that in mind. Okay. We will discuss a system of linear equations in n unknowns x1, x2, xn. In this system, is written in this fashion. The first equation is written as a11x1 plus a12x2 plus a1n xn equal to b1. Second equation is written as a21x1 plus a22x2 plus a2n xn equal to b2, and so on. And finally, we write the mth equation in the same fashion. This notation is used so that we can write this system of m equations in n unknowns in matrix form, and we extract the coefficients a, j, k of this system of linear equations and record them in a matrix A, which is m by n, and let x be the column vector of unknowns x1 up to xn, and b is the column vector of known quantities b1 up to bm, and the the equation, the system of linear equations amounts to writing the matrix equation Ax equal to B. So m equations in n unknowns can be written in very compact form as Ax equal to B. The matrix A is called the coefficient matrix, and a vector C with n components is called a solution of Ax equal to B if AC equal to B. If B equal to 0, then Ax equal to 0. This is called a homogeneous linear system, and the homogeneous linear system has a zero solution because A times 0 is 0. You can check by using matrix multiplication that A times 0 is the 0 vector, and therefore homogeneous linear systems are always consistent. A general solution Ax equal to B may not be consistent. Now, if C1, CR are solutions of Ax equal to 0, then we can take a linear combination alpha 1 C1 plus alpha R CR, and this is also a solution of the same system of equations, homogeneous system of linear equations, because A times alpha 1 C1 plus alpha R CR by properties of matrix multiplication and linear combinations, it is equal to alpha 1 AC1 plus alpha R ACR, and that is equal to 0. A general linear system has B as a arbitrary vector, and this is called a non-homogeneous system if B is not equal to 0. Now, a non-homogeneous system may have no solution, one solution, or infinitely many solutions. This linear system, x1 plus x2 equal to 1 and 2x1 plus 2x2 equal to 1, doesn't have a solution because these two linear equations actually represent two lines, and these are parallel lines because their slopes are equal. So two systems, two linear equations in two unknowns may have no solution. But look at the equations x1 plus x2 equal to 1 and x1 minus x2 equal to 0. This has a unique solution. These are two lines in the plane and they are intersecting in a unique point, namely a half comma half. So these two equations in two unknowns have a unique solution, and it is a non-homogeneous system of equations. We can write down a general system, the general solution of x1 plus x2 equal to 1 and 2x1 plus 2x equal to 2 in terms of real numbers. These two equations have infinitely many solutions because geometrically these are exactly the same line. So these two lines coincide, and therefore we expect infinitely many solutions, and we can write down the infinitely many solutions by substituting arbitrary value of x1 equal to alpha, and then x2 becomes 1 minus alpha, and therefore there are infinitely many solutions. So just this simple case of two unknowns and two linear equations tells us three possibilities for solutions: no solution, or one solution, or infinitely many solutions. There are no other cases of solutions of systems of linear equations. We will soon prove this fact for arbitrary system of linear equations, that either there is no solution, or there is a unique solution, or there are infinitely many solutions. So we want to now break up the problem of solving system of linear equations into two parts. First, you look at the homogeneous system of linear equations Ax equal to 0. And by some means, suppose we know the set of all solutions. So let S be the set of all solutions of Ax equal to 0. And our system of linear equation is Ax equal to B. We find one solution of Ax equal to B. One solution of Ax equal to B is called a particular solution. Then the set of all solutions of the general system Ax equal to B is obtained by adding all the solutions of Ax equal to 0 with the particular vector C. So add C to each and every solution of Ax equal to 0, then the resulting set of vectors is the set of all solutions of Ax equal to B. So let us pick an element C plus S, where S is one solution of Ax equal to 0 and C is a solution of Ax equal to B. Then A times C plus S is AC plus AS. AC is equal to B because C is a solution of Ax equal to B, and AS equal to 0 because S is a solution of Ax equal to 0. And therefore A times C plus S is B, and that shows that C plus S is a solution of Ax equal to B. Now we prove the converse. we want to show that every solution of Ax equal to B looks like C plus S, where S is a solution of Ax equal to 0. So suppose we subtract the vector C, which is a particular solution, from an arbitrary solution of Ax equal to B. So look at A times x minus C, that is Ax minus AC. This is B minus B, this is 0. And therefore, x minus C, whenever x is a solution of Ax equal to B, x minus C is a solution of the homogeneous system, and therefore x minus C must belong to the set S, and therefore x is equal to C plus S for some S in this set S. So this shows that the set consisting of C plus S, where S is varying over the set S, is the set of all solutions of the general system of linear equations Ax equal to B. Therefore, the problem of computing all solutions of a system of linear equations is broken into two sub-problems. The first problem is to write down all solutions of the corresponding homogeneous system Ax equal to 0. The second problem is to find one particular solution of Ax equal to B, and then suppose C is that particular solution, we can translate all the vectors in the set S by this fixed vector C to get all solutions of Ax equal to B. So let us now discuss a particular case of system of linear equations. We will see that this particular case gives us enough experience to tackle the general case. So in this particular case, the coefficient matrix is upper triangular and its diagonal elements are non-zero. So we have n equations in n unknowns. The first equation have all the variables x1 up to xn. The second equation doesn't have x1 in it. The third equation will not have x1, x2, x in it, and so on. The last equation has only one variable xn. So as we move down, one variable disappears from the equation at a time, and finally the last equation has one variable only, a and xn, and we are assuming that the coefficient matrix is upper triangular and the diagonal entries are non-zero, and therefore we start with the last equation a and n xn equal to bn, and we can solve for xn, and xn is uniquely determined from the last equation. Then we go back and substitute xn in the n minus first equation, and that says that xn minus 1 is uniquely determined. Then substitute xn and xn minus 1 in the n minus second equation, and that will say that xn minus 2 is uniquely determined in terms of xn and xn minus 1, and so on. And finally x2 is uniquely determined from the second equation, and go back and substitute in the first equation, and we can get value of x1. So this system of n equations in n unknowns, where the coefficient matrix is upper triangular and diagonal entries are non-zero, has a unique solution. And we now look at a general system of linear equations and try to convert this into a system which is similar to this. Okay. Now, if you have a homogeneous system Ax equal to 0, that has only the 0 solution. Therefore, it is a consistent system, and so the set S in this case consists of a singleton, namely the 0 vector. And so if Ax equal to B has a solution, then it will say that this has a unique solution. Yeah? Because all solutions of Ax equal to B are obtained by simply translating one solution by each and every solution of Ax equal to 0. But if Ax equal to 0 has only the 0 solution, then Ax equal to B will have a unique solution. Now we take Q from this special case of an upper triangular matrix, and we will transform any m by n matrix into an upper triangular form and use this method of back substitution to arrive at a solution of a general system of equations. So above process can be carried out without writing down the entire linear system. We simply look at what is called the augmented matrix. The augmented matrix is obtained by simply adding the B vector as a last column to the coefficient matrix, and the first row will be the first row of A along with B1, the second row is the second row of A along with B2, and so on. So we construct this augmented matrix. So the entire information about the system of linear equation is contained in this augmented matrix. We will now try to modify the augmented matrix by what are called row operations. And these row operations are not going to change the set of solutions. They will change the system of linear equations, but they will not change the set of solutions. Using the row operations, we try to simplify the augmented matrix so that at the end it becomes a upper triangular matrix. And once we have an upper triangular matrix, then the corresponding system of linear equations can be solved by the backward substitution process.